All right. So at the start of last Wednesday, we said today, well, first thing we're going to do is go over the exam. So let's go ahead and do that, and then we can, I know there's some questions on the homework, so we can come back and talk about those. And then hopefully we'll get to 3 reservoir problems as well. Okay. All righty, so on the exam, for those that haven't had me for a traditional class before, let me talk a little bit about how I grade exams. Okay. So on the exams, I have a cover sheet, and it's not because I want to kill trees or anything like that. It's because I have you, well, to give information about the exam, obviously, but also for your name goes on the cover sheet, and then I go through before I grade and I flip the cover sheet over, and the tests become all mixed up. And that way, when I'm grading problems, I don't know whose test I'm grading. So I'm trying to eliminate any biased, unintentional or intentional, hopefully there's no intentional there, but unintentional bias on, oh, this is so-and-so's, you know, I'm going to score them really good because I really like them. Or, you know, I am kind of being a little cheesy there because I don't think I have anything against anyone in here, but still, you know, I want to try to eliminate that. And then I grade all of problem number 1, and I try to take the same number of points off for the same mistakes. But that's a little hard sometimes because students get creative. And I do miss things because students in exams, when you're stressed, you start writing all over the place, you know, and solve part of the problem here, and then you come up here and I'm trying to climb inside your head and figure out what you did. So I don't disagree that I do make mistakes. So if you have concept questions while we're going through the exam today, please ask them. If you have questions about your score, please come see me individually, all right? And I'll be happy to go through and see if I did make a mistake or explain to you why I felt like this is why I took off that many points. Because there's certain things that I do feel have a certain value to them. So with that, let's go ahead and move through this. I'm just going to rather than me sit up here and write it down, I'm going to put it up here and we'll talk through it a little bit. Hopefully that'll show up okay, and then we can zoom in a little bit there. So we've got this reservoir system, 2 tanks. We know the length, we know the diameter, we know the minor loss coefficients, but we don't know the elevation difference between the 2 tanks, all right? So the first goal is to find the friction factor, show your work on the attached Mooney diagram. So I did expect to see something on the Mooney diagram. If you wanted to use the equation, that was perfectly fine. And if you use the equation correctly, you should get the same answer, all right? Or pretty close to the same. Realizing that it's really hard in the exam if you don't have a straight edge and you're in a hurry. Question, okay? You never got your exam? Because I thought that I'd emailed, oh wait. There's 2 that I didn't give to the grader. Whoops, and one of them is yours, and the other one's not here. TJ, I apologize. I did email, had the exams emailed, but your 2 got stuck somewhere. So I'll try and get yours out right after class. But everyone else get a copy of theirs? You can pick up my office. It should have been emailed, except for TJ's where I made a mistake there. All right. So we have to use the Mooney diagram to find the friction factor. All right. Now I don't know what it was, but and I didn't write it down here, but there was probably 6 to 8 of you. I didn't keep track of the total, but there was an awful lot of people that I think wrote the Reynolds number as Q times D divided by the velocity times the kinematic viscosity. And I'm not sure where that came from, but like I say, there was a good number of students, and it's really surprising to me, one, that you have a card where you can have the equations in front of you and you get the wrong equation. Not a lot I can do about that, you know, and I don't even know where this equation came from because that is not a dimensionless parameter. And so you might, you know, I think I took out 3 points there. And it was pretty hard because this is something you've seen in fluids. We've used it multiple times here. You have an equation card. I think there's only 2 points, but you should be able to get that, right? You should be able to calculate the Reynolds number. So that is not a dimensionless parameter. And I can't remember if that was exactly, but it was a bunch of students that had the same wrong equation for the Reynolds number. All right. So knowing the roughness coefficient, K sub S, and the diameter, we can come down here, we can find E over D, and you need to be careful with your conversions. 10 centimeters, 0.1 meters, gives us 0.004 as far as E over D, and then the Reynolds number, velocity times diameter divided by the kinematic viscosity, or if you want to use the flow rate, that's fine, you can use that one. And we get a Reynolds number of about 2.5 times 10 to the 5th. So we come over to the Moody diagram. That's good, all right. So there's 1 times 10 to the 4, 1 times 10 to the 5. There's 2, and if you come, there's 4, so 3 is in here, so 2.5 is going to be right there. I'm going to identify my E over D right here. I'm going to follow that line up because we track the line until it intersects with the Reynolds number. And when they intersect, then we come straight over, and you should have got a friction factor somewhere around 0.018. And I wasn't too critical of that because I know this is during an exam. So if your line didn't come over, if you know, if you're at 0.017, even 0.016, as long as I could see that you had these 2 values correctly done and your line was just off there. All right, so given that now once we have the Moody diagram or the friction factor, we can come in with our energy equation and we can put in our minor losses. Everything here is a function of the velocity head. So what I have is Z1, and I set my datum equal to, or my data, I set datum at Z2, but you didn't have to, as long as you realize that Z1 minus Z2 gives me my delta Z, and that's what we're looking for. So going ahead and solving this equation, I come up with a delta Z of 3.69 meters. You know, round off there a little bit, so as long as you're close to that, that's good. And then we talked about the Hayes-Williams equation. If we want to use Hayes-Williams and we have minor losses involved in Hayes-Williams, we even go back to the Colebrook-White concept, I should say the Darcy-Weisbach concept, to calculate that. And so that's where we have the minor loss coefficient of the valve is equal to F L over D, and all we have to do is solve for L. And that gives me that for a minor loss coefficient of 5, for a pipeline that has a friction factor of 0.018, my length is approximately 28 meters. Okay. Any questions on that problem? This is a great time to ask them because we are still using these concepts. Okay, problem number 2 is an opportunity to show me that you know how to calculate the momentum correction coefficient. All right, once again, several of you used the energy correction coefficient equation, which is the wrong equation. Very similar, of course, but this is the equation. There are other forms of the equation. And I'm fine if you use the other forms of the equation, but make sure you use them correctly. Because some of you apparently grabbed an equation out of the book, but you didn't understand it. And so you used it wrong, and which gave you the wrong answer. So the equation in the book, which is slightly modified, it's just things have been moved around a little bit, will give you the same answer if it is used correctly. So we're going to take the sum of the individual velocity squared times the area. and divide that by the average velocity times the total area, okay? Where V is equal to Q divided by A. So I went in there and I calculated the individual velocities for V1, V2. Here's 1, here's 2, and here's 3. Calculated those. And realized that then V average, okay, right here, this is another big area that a lot of people miss. V average is the total flow rate divided by the total area. It's not the average of the 3 individual velocities. You have to take the whole flow rate divided by the whole area to get the average velocity across the whole cross section. So once we do that, then we just go ahead and plug it into that equation up there. And so you can see my individual parts here, V1 squared times A1, everything for 2, everything for 3, divided by the average velocity squared times the total area, gives me a beta of 1.16. Okay. And if you're ever doing energy correction coefficients and you get an energy correction coefficient or a momentum correction coefficient less than 1, you've done something wrong. And if it's ever greater than 2, you've most likely done something wrong as well. It should be between 1 and 2 for the most part. There are some rare cases where it may go higher than 2, but they're pretty extreme. Any questions on that? Any questions from those online? Okay. EGL and HGL. I was looking for some key concepts here. The things I was looking for was that, so EGL, let me just take a step back, all right? Remember, EGL and HGLs are only representative of what's going on in our system. They don't have to be exact, but they should be fairly close, all right? And I tried to make these fairly close by telling you what the pump EGL would be up there, so everyone went to the same point there. So everyone should have the 3 common points. The water surface elevation at reservoir 1 and the free discharge of the pipe. The HGL always starts at the reservoir when there's no velocity and it goes through any kind of a free jet. The pump EGL is going to, that's the amount of energy the pump is going to add right there. The other things I was looking for, that because D2 is greater than, D2 is less than D1, we know then that V sub 2 is greater than V sub 1. And I've written it down there in terms of the velocity head, so it doesn't matter. But I was looking to see if your velocity head there was bigger than the velocity head there, because that difference represents the velocity head, okay? So entrance loss coming down there, the slope, this isn't very, it's not accentuated on mine, but the slope of the lines over here at D1 should be less than the slopes at D2 because the friction loss in D2 is greater, hence the slope is greater. And it is true that for mine, but it's not very accentuated. I probably should have flattened these out a little bit more and make them a little more accentuated. So I was looking for difference there, difference in the slope, the fact that you went through the free discharge down here, and given the fact that if you went from there to there, your hydraulic grade line is going to be under point A, and so the concept here for the second part of that problem is what can you say about the pressure at point A? It's going to be a vacuum, it's going to be negative because the HGL is underneath the elevation of that point, and that's what I was looking for right there. Okay, questions on EGLs and HGLs? These are powerful concepts that we will continue to use as we do 3 reservoir problems and pipe networks. Okay, you guys are being awfully quiet today. Yes?
What exactly is the difference between the EGL and the HGL?
The velocity head. Okay. So if you think about the energy equation, this right here is the HGL. and everything together is the EGL. So the difference between them is the velocity head.
And what does P over rho represent?
P over gamma,
Yeah.
your pressure head. That's the pressure head you have in your system. Okay? All right. So on this problem right here, you have a gate that is held up, well, a gate that's holding back water, and there is a cable attached to the top of it that goes over a pulley, that goes down to a concrete block, and we want to find the minimum amount of concrete that just barely keeps that gate up. If we added 1 cup of water, then that gate would start to open because the force on the gate would overcome the force on the block that's in there, all right? And I gave you a hint here, remember buoyancy force on the block, take that into account because that's easy to miss. So, first thing we find is the pressure force, pressure is equal to gamma. HCI, you see I had a mistake there, that should be times the area as well. So I did it down here, but I missed my equation. So gamma HC times A. Little hint here. When I'm giving exams, you are more than welcome to draw on the diagram itself. On homework, I want you to draw free body diagrams. And on this one, you should have drawn some mini free body diagrams, but there's nothing wrong with coming in here and saying, you know, I know there's a pressure distribution like this on the gate. Okay, if that helps you out. And I can find then the pressure force by gamma HC times A. HC is the centroid of the gate, not the centroid of the pressure distribution diagram. Centroid of the gate, okay? The gate is 8 feet tall, so the centroid is halfway down, because that's where the centroid of the rectangle is at. So knowing that, we can now calculate the location of the pressure force. And if you remember, and this was fine, if you remembered, I didn't need the equation, if you remembered that the pressure force acts through the centroid of the triangle of the pressure force distribution diagram. And that means that this distance here is 1/3 h. Now, if you go ahead and use the equation, you're going to find out, what did I do there? Oh, 16 seconds, okay. You're going to find out that it is actually 2/3 down this way, or in this case, because it is 8 feet tall, it occurs at 16/3 feet down from the top. Remember, the LP measures from the top, okay? So the equation is going to give you 2/3 of h right there, hence the 16/3, and you could have just used that, and I would have been fine with that. But now that we know the forces on the gate, we can now draw a free body diagram of the gate to calculate what's going on up there in that cable. So down here, I did a quick free body diagram. I've got the hinge down here. Now, technically speaking, there would be a force right here on the hinge too, right? Force in the x direction on the hinge. So I've got 2 unknowns, but in order to get rid of one of them, I can take the sum of the moments about this point to find the tension. Or if you wanted to, you could take the sum of the moments about the tension, about up here, and calculate the force at the hinge, and then you can take the sum of the forces in the x direction and get T, right? That's just the longer way of doing it. Think back to basic statics. We've got those 2 well, we got 3 if you want to take some of the forces in the y, 2D problem. So you could have done one extra step and still found it by taking the sum of the moments about T, but the easiest way is to do it about the hinge, because it gets rid of this one, which I don't care about. Now I can find T. T is 2662. And once I find that, now I can draw another free body diagram over to my block, noting that I have a tension pulling up, I have weight of the concrete pulling down, and I've got the buoyancy force also trying to lift the block. So some of the forces in the y direction, noting that the weight component is the weight of the concrete times the volume. The buoyancy force is the weight of the fluid that is displaced times the displaced volume, and they happen to be the same volumes, just different gammas. So now I can go ahead and put that in my equation, and I can solve for my volume, and it's right around 30.4 cubic feet. Okay. Any questions about the concepts?
Mr. Brooks,
Yes.
how did we get the 10? Why multiply with 10 some?
How did I find T, the tension?
No, the 10. Value 10.
Well, the value of 10. The value of 10 comes from the fact that I know that the gate, or the water level, I should say, the water level right here is 8 feet, and the gate where the cable connects is 2 feet above it. So that's where the 10 comes from, yeah. Okay. Other questions? Okay. All right, so let's move on. But once again, if you have questions about how I scored your exam, feel free to contact me. We can talk about it. We can do it over Zoom. We can do it in my office, whatever you're more comfortable with, to make that happen. Okay. All right. So question on 4, 5, 6. Okay. And to be honest, I don't even remember. So let's bring it up here really fast. There's my quick links. We don't have Adobe on here.
Yeah, it's up at the top, you say okay.
Oh, thank you. Okay. All right. Okay, so assume that the pressure difference between points 1 and 2. Oh, wait. Is that the one?
Yeah.
Okay. Assume the pressure points between 1 and 2 is 30 psi. What will be the flow rate? All right, the pipes are galvanized iron. We got that. Okay, so it's coming back to me now. So this is the scenario when we know the head differential between these points, but we don't know the flow rate. So we're trying to find, obviously, and we need the flow rate to calculate the Reynolds number to be able to find the friction factor. So this is a complex problem that now requires you to iterate on a branch network. So you're solving this branch multiple times. So you have to make some guess as to either friction factor or the flow rate in each one of those pipes to get an initial value, all right? And so while it seems like it's not that, you look at it and says it's pretty simple, the pipe comes in, splits into two, and goes over, it becomes kind of an accounting mess because you've got so much going on, right? Now there are ways to solve this where it is not so bad. If you have access to a solver like Excel or some other solver, but so pipe comes in here, splits goes over here. And we got this point down here. Okay, so if this is point 1 and this is point 2, our major equation then is going to be the energy equation. Between points 1 and 2, noting then that our head loss has to be the loss, I forgot, how are these numbered?
A,
So this one's A,
and
B,
C,
and then-
that's for,
or is this one A? Sorry.
no, that's not even A.
Oh, okay, good, because we don't need that, yeah. Okay, so noting then that the head loss is going to be either up around A and over to point 2 through C or B. So plus then F, and if I take the top route, F sub A times L sub A divided by D sub A times V sub A squared over 2G plus then F sub C times L sub C divided by D sub C times V sub C squared over 2G. Okay. So that now gives us one equation. But we also note then that that the head loss across A is equal to the head loss across B, right? We know that. So I could just as easily replace this in here with the head loss at B, because they would be the same thing. Doesn't matter if I'm going across A or across B. And then the other equation I'm going to need to know is what is the relationship, and so between those, I know that Q sub A plus Q sub B is equal to Q sub C, which you could rewrite as B sub A times A sub A plus B sub B times A sub B equals B sub C times A sub C. Okay. And we identify then what are our unknowns. Well, the unknowns are B sub A, B sub B, and B sub C. That's what our unknowns
And
are.
all of our friction factors.
Now, our friction factors are unknown too, but if we have our velocities, then we know our friction factors. So this, we're back to that, what we did with the single pipeline is, yes, these are unknown, but now we have to iterate. So once again, we select a friction factor. We stick that friction factor in here, and we can solve through these relationships what our velocities are. Okay, now we're going to take our velocities and E over D and go back and refine our friction factor. And then we're going to do the whole process again until it converges.
So you would assume a friction factor for A and B and C that are all the same, because they'd likely be different.
You could either do the same or different, doesn't
Right.
matter.
But if you overestimate A, that's going to potentially reduce B and C. So how do you know which way to move?
You don't have to know which way to move. The equations automatically fix it for you,
Okay,
because you're going to find, once you assume a friction factor, it's going to give you a flow rate. That flow rate, you're going to find a Reynolds number, and then with that Reynolds number, you're going to go in Moody, and then you're going to be able to, it will tell you which way it goes. Okay, it will automatically adjust. Now, if you're saying, wow, would we really do this in practice? Well, no, in reality, we have equations for the friction factors, right? We would put Swami and Jane in there, or the Colbrook-White equation if you want to get really, really fancy. So if we say that these are really unknown, if our friction factors are unknown, well, our equations to solve for those are the 3 friction equations. But they now introduce 3 more unknowns. I guess they're really already there. The Reynolds number, right? So now we have to write the Reynolds number for 3 different pipes. So in reality, there are 9 unknowns to this problem, and you could solve it inside of like a spreadsheet by writing the equations and then just saying, okay, solve it. Now I'm going to solve it as a system, and it would, boom, give you the answer. Now, we haven't really talked about how to solve things as a system in this class. I think everyone in here has taken civil tools, right? Remember the solver? Okay, what's that?
I'm in it.
Oh, you're in it now. Okay, so you haven't seen it yet, and that's fine, because it's not that difficult. But the solver inside of Excel would make short work of this, and we are going to use that in this class. Now, typically, for problems for undergraduate students, this one I wanted to stretch you a little bit, but for like exams or for when we get into bigger problems, I wouldn't have you find the friction factor. I'll give you the friction factor. Like the first problem in the homework, I gave you 3 of the friction factors because like having you guys work 2 problems where you got to find the friction factor over and over again becomes just a pain, right? I mean, you're there 2 hours going back and forth. But I wanted you to at least experience it with a 2-pipe branch to see really what are the details of this type of a problem. Okay?
I have a quick question.
Sure.
So you were given the K factor for the pipes. Could you have used the Hayes and Williams equation to get like a really, really conservative friction factor?
Okay. So that's a really good question, and I think this points out where we need to be really careful. Let me come back to this problem here. So they gave us the K. What's that? Sorry.
No, I mean, your cursor is down on 4.5.7. We're up on 6.
Oh, thank you. All right, so they give you a K factor. Tammy, I'm not trying to single you out here, but when you say they gave you a K factor, tell me in your mind how this correlates back to Hayes and Williams.
The friction factor is equal to L over D, or the friction factor times L over D is equal to K.
Okay, so all right, so good. You helped explain here. So we need to make sure that we clearly understand that the K in this problem is the equivalent sand roughness, which is completely different than the minor loss coefficient. The equivalent sand roughness is the average height of the sand particles. Okay, so that is not the K that we would bring it back to. But nonetheless, Cami raises a really good point. While the K is different, what we do know is that this is galvanized iron. So if you wanted to, you could actually go into a chart and find the Hayes and Williams coefficient, C sub HW, for galvanized iron, and you could write the Hayes and Williams equations for friction losses across each one of these pipes, and it would be a whole lot easier because it would fall right out and you wouldn't have to iterate. And that's the beauty of the Hayes and Williams equation, as inaccurate as it is, or as it's an empirical equation, even though it's an empirical equation. So it's not dimensionally homogeneous unless we put that correction coefficient on there. But it works pretty good, and it's a whole lot easier, and that's why people used it. But now that we have other tools available to us, a computer, we can actually narrow it down a little better than the Hayes and Williams. But the Hayes and Williams would be a simpler way of solving this problem. So I'm glad you brought that up, because that just kind of highlights why they liked the Hayes and Williams back in the day when they didn't have a lot of tools to help them solve these problems. Okay? But make sure you clearly understand that K, the sand lot, or the sand equivalent diameter, or the equivalent roughness height, is not a minor loss coefficient. All right, other questions on this? Anyone online have questions?
Could you maybe go over the first homework problem a little bit?
Okay, sure. So let me jump back up here. And so actually, the first homework problem is exactly the same as the one we just went over, except for now there's 3 pipes. And rather than iterate, I gave you the friction factor for the first 3 pipes. So let's hurry and bring this up here. This pipe comes in, and I'll turn this back on for those online here in just a second. So, and for those here, I guess, just give me a minute here to do a quick sketch. Okay, I think this is a little different in that they give us the flow rate, right? Okay, so in this case, the flow rate is known, 0.5, okay. Q is equal to 0.5 meters per second. Now, jump back to this. All right. So this is kind of the same thing. I'm going to write the energy equation from point 1 to point 2. Okay, and I'm going to note my head loss is then a function of whatever path I take, whether I go across A, whether I go across B, or whether I go across C. So it's going to, let's say A again. So F sub A times L sub A divided by D sub A times V sub A squared divided by 2G plus F sub D times L sub A times D sub, not A, sorry, L sub D, D sub D times V sub D divided by 2G. All right. Noting that this right, no, not that one. Oh, that's not right. Erase the pen, sorry. Noting that this one right here could be replaced by F sub B times L sub B divided by D sub B times V sub B squared over 2G, or F sub C times L sub C divided by D sub C times V sub C squared divided by 2G. Okay, wouldn't matter. I could use any one of those in there. Okay, and I can also note then that the hydraulic loss across A is equal to the hydraulic, or the head loss. Sorry, the head loss across A is equal to head loss across B, which is equal to the head loss across C, which is then essentially saying these three things right there are equal. And I also know that Q sub A plus Q sub B plus Q sub C equals 0.5 cubic meters per second. So that's kind of my knowns there, right? Now note, I gave you these three values right here. What I did not give you was F sub D, but we know the flow rate and we know the roughness height. So now we can find F sub D using Moody or the equation. So F sub D now is a known. We know that. Okay. And so now it's basically the same process as the other problem, in that I can go ahead and solve for these equations, this one right here, realizing that all three of these are equivalent, and noting this right here, I have three unknowns, the velocities, rewriting this as V sub A times A sub A plus V sub B times A sub B plus V sub C times A sub C, right, equals 0.5. So I can rewrite that in that term. So my three unknowns in this case, and there are no frictions that are unknown. And Q sub D is not unknown. So my three unknowns are the three flow rates, and I have my three equations, 1, 2, and 3. Okay, so Laura, does that help a little bit? Okay, I don't think you're still muted. Laura, did you say
Yeah,
something?
that helps. Sorry, I forgot to unmute.
That's fine. Joys of technology. All right. So I tell you what, it seems like we had a little bit of problem with this, but my office, do you guys have class at 9? Are my office hours at a bad time? Okay, you just want to make sure, you know, but anyway, since it seems like there's quite a few questions about this, I will give you more time to work on this. If you want to keep working on this homework, okay? So that's not a problem. All right. Any other questions? Okay, we're not done yet. It's a good quality time here. One of my favorite sayings about higher education, the only place you're willing to pay more to get less, right? Passing down the road, is it gonna be okay? Yeah, no, not right there. So for those online, this is posted to Moodle, so you can print off a copy. Although we're not going to get all the way through it, but at least we kind of set it up today. So we have a 3 reservoir problem here, and I wanted to work through the numbers. Okay. So given the 3 reservoir setup, ignoring minor losses, solve for the flow rates in the 3 pipes, the pressure or the hydraulic grade line at J, and the pressure at the junction as well. So noting that I've got my water surface elevation is equal to my hydraulic grade line. Excuse me. So what I'm saying is A right here is 235. B over here is at 200 feet. And C is, I'm sorry, that's 235. B is at 235. And C is at 200. 250, thank you. So, you know, it's kind of interesting that wearing glasses with this shield kind of does distort everything a little weird. It's because it's bent, and I'm going to use that as my excuse. Whether I should or not, I'm going to keep it at that. But all right, so when we look at this, tell me, what are the directions of flow in this system that we absolutely know? Okay, going down from A? Okay, so A is definitely going down here because it's the highest amount of energy. Okay. And from there, what else?
Flowing into C.
Okay, so it's flowing into C. Can we say anything about B? We don't know, right? We don't know whether the flow is going from B or to B. Or in other words, to B or not to B. Sorry. So that's what we need to figure out here. And in order to do that, we can now try and simplify our problem a little bit by first finding the C value, okay? Remember, we said that C is equal to F L over D times 1 over 2G A squared plus the sum of the minor losses times 1 over 2G A squared, okay? In simple terms, assuming that it's all the same diameter of that pipe. Now, in this particular problem, we've said that we're going to ignore minor losses to kind of keep our life simple. So I can go ahead and solve for my different C values. So C sub 1 is going to be equal to 0.018 times L, which is going to be 1400 divided by the diameter. Make sure you use the right units. It's 10 inches divided by 12 to get it into feet, to make that dimensionless. And then 1 over 2G 32.2 times the area, which is going to be pi divided by 4 times 10 divided by 12 squared. Then I'm going to square my area as well. And when I do that calculation, I'm going to get 1.58. Okay. So C sub 1, if you will, then is 1.58. Now I could do this exact same thing for pipe 2 and pipe 3, plug everything into this equation. When I do that, I'm going to find out that C sub 2 is 3.09 and C sub 3 is 33.83. Okay. From here, I can now set up my equations to calculate the flow. Let's do this really quick. The hydraulic grade line at A, and I'm assuming I know the flow direction, so I'm going with the hydraulic grade line, going down slope, so I'm losing energy, minus then C sub 1 times Q sub 1 squared is going to give me the hydraulic grade line at the junction. And then I can start at the junction, and I say the hydraulic grade line at the junction minus C sub 3 times Q sub 3 squared is going to give me the hydraulic grade line at C. And then the one at B, I could write that multiple ways, but let's just stay with the hydraulic grade line at the junction. So the hydraulic grade line at the junction plus or minus the friction loss, C2 times Q sub 2 squared, is going to get me to the hydraulic grade line at B. So now I have my three energy equations. We can add on our continuity equation, and we'll do that when we come back on Monday, okay? So I will make the homework, the homework that was due today, I will make that due Monday. I did post homework with the 3 reservoir problem due Tuesday. I will change that because we haven't went through far enough here. So I'll change that. That one will be due Wednesday, all right? And we'll finish this problem on Monday. So have a great weekend, and we'll see you on Monday. Okay.
Thank you.
All right, you better have a great weekend.